digital twins for ocean robots and marine ecosystems. So I'm aiming here to kind of give you both a bit of a flavor of what digital twins are, what they might be useful for us in the context of ocean and climate science, and sort of illustrate this through kind of my own work and collaborations. So there is a number of definitions for what this digital twins concept is that you'll find online. I put a few links here. Maybe the best place to start is in Wikipedia, where you will see different bit of the history and some context. I think most people sort of point as the beginning of this notion to NASA work in the 70s and 60s. The Apollo 13 mission is often mentioned as kind of this first real life application where really people wanted to have a virtual representation of what the mission might look like in order to test it in kind of complex circumstances and design it. So then there is definitions that range more from the engineering side, where this is a kind of a very useful common concept, this digital twin idea, to more the climate side. And I listed at the end here a presentation that I found from Catherine Wilcox a couple years ago, I think, that sort of goes into this in more details. So rather than trying to give you kind of pass this down to a uniform definition, which I don't think I'm really able to do, I'm going to give you the one I'm using to make things more concrete. And so what we're talking about is having a computer representation of real systems that then users can interact with, and having a two-way connection between the real system and the virtual one. So there's going to be observations, for example, and then a modeling of that. In our case, the real system really is both the climate system and the observing network that we use to monitor it. And so that's the real system that we want to simulate, meaning something like Argo under climate scenarios, how we behave, what we observe. We want to simulate that. And being able to compare with the real observations and the mutual benefits, the two-way interaction is kind of key. So I'll highlight it in a couple different ways. The first one is what people refer to as data assimilation. So that's an example here from a while ago. This is from my work, my PhD work. So this was a demonstration of the potential of the Argo array of floats as a monitoring system for the AMOC, or the ocean circulation in general. And so what you do is you create a little scenario where you have, a climate perturbation. Here, this is the left-hand side column, for example, that represents this. These are anomalies of the barotropic stream function and the meridional overturning stream function. You have this sort of simulated future, and then you simulate something like Argo, which is what I did, and then you try and use it to kind of get back to the variables you want. And so in this case, I did kind of a data simulation into a model to show that by the end of that process, once you have accounted for the new data being collected, you go from the left column to the right column, meaning you have reduced the uncertainty in, say, the AMOC by collecting a bunch of temperature and salinity profiles that are related to that in a way that's not trivial. So this is an example from this paper. I picked a somewhat old one to illustrate that this is something we've been doing for a long time in climate science. There's a literature on what's called observing simulation experiments like this, or more simply, observing system simulation experiments, which we've touched on in the context of this webinar series before, with regard to efforts simulating SWOT, for example, using models. So why digital twins for ocean robots? This was an example, right? Can we make a case that Argo observes the AMOC? Yes, we can. Then here is another example, more recent. So this is a picture of a collective that gathered last summer to discuss different strategies that we could envision to observe the ocean. There are people here that you know, a bunch of US folks, a bunch of internationals, but a mix of people that do like technology development, developing sensors and robots, to people that do kind of modeling, either from the mechanistic side or the AI side. And so there is a real need as we design new and better ways to observe the ocean for kind of a modeling framework, a digital twin framework to anticipate and demonstrate the value of the future observations, for example, or just to simulate them in certain cases that are complex. So there's a lot of demand for this sort of things today, I would say. What do I mean by ocean robots? This is from the time that I was putting together Eco version 4. I mean, all of the in situ data sets we already have collected, for example, that's on the right-hand side, but also a whole bunch of satellite data, which I guess I could call space robots observing the ocean, but I'm just putting on the ocean robots for simplicity. I want to simulate all of those and to zoom in on the more recent stuff I've been doing. Here are a list of ocean robots to which we now have kind of easy interface to, and we can simulate as well. There is a reference to a Julia package here that I need to mention once more, for oceanrobots.gl. Here is a list of Julia packages that you can use today to access all sorts of data sets like this. Oceanrobots.gl I'm going to show in a minute. There's more on Argo data, a bunch of others. Ocean state estimation is to access ocean analysis products, reader data sets. And so here is what's inside oceanrobots.gl at this point. So you'll see that these are various programs that are carried out by the international community and sponsored by the US, either NOAA, NSF, or NASA, depending on which one. So the NOAA buoys, for example, are there, Argo and the Drifter program, as well as a satellite altimetry example. So I would say all of those we have kind of easy ways to access at this point in different languages. These are sort of what I use, but you'll find more. And so I've told you about ocean robots, what I mean by that, where the data is and how we access it. I'm going to tell you more about how we simulate these data sets. And so this comes to the computer representation of this data, as well as the climate system. So I've already said this, but I'm going to start from the climate system itself and go all the way down to simulating sensors. And I'm going to start with a slight detour to highlight the interactivity. So the interactivity, in a way, is what's new compared to what we were doing before. At least that's one of the new aspects. Integration with cloud computing is another. But so interactivity is kind of key because you want to be able to look at climate and data in a way that's convenient and kind of game-like, ultimately. And so this is an example from a notebook. In this case, we're looking at an interactive visualization of ocean state estimate called ECHO. And I'm going to show you this one a little more, slightly different way, just because I want you to see the interaction I'm referring to. So this is an example of a notebook that is a so-called Pluto notebook. And so the whole point of this is they are easy to generate. You don't see the code because I had it from you for display, but they are interactive in the following way that you just change the name of the variable, you click, and you can decide that you want to zoom in somewhere. I guess this doesn't zoom well, but this does. Change variable, change solutions in this case. So this is the sort of tools that have emerged over the past few years that I think is worth highlighting. This is all open source, of course, and the type of framework that I think we're going to get used more and more to driving models with. And so this is, if I go back to my slide, this sort of interactivity applied to now running models is what I introduced in this presentation a couple of years ago now at JuliaCon. And so there is this climate models GL package that I have that I use to drive a bunch of different models. And these models might be of different languages. Ultimately, it does not matter much. Some are Fortran, some are Julia, some are Python, C, whatever. So there's a little video for you to watch, but I was going to just dive in and tell you about the model hierarchy that I'm considering in the context of this work. And so it starts with climate models.jl as kind of the driver for all of those things. And then we're going to go and sort of build a typical workflow that we can imagine. So the workflow would start with, let's pick a future climate. And so we're going to use here a little climate model emulator. I think this one is called Hector. There's another one called Fair, and there's a bunch more. So these are emulators, I should stress, meaning they go very fast and they generate, depending on the parameters you set, a future climate scenario for you. So you can take this and then you can apply it to something like echo to, say, redistribute the heat uptake. And this is what's depicted here. This plot is from a paper I did a couple years ago with David Ferreira. This is using echo, the global ocean state estimate, to redistribute the heat. Once you have this, you can start simulating the ocean robots. And so typically, this goes through a Lagrangian simulation framework, which is an example is shown here. This is a bunch of virtual particles or instruments that I'm letting drift in an ocean model, in the case of climatology of the ocean circulation from ECHO. And this is done here at near the sea surface. So you see the kind of the convergence of those pathways, which should remind you of the problem of convergence of plastics in the ocean, because it's kind of the same problem. But say that could be a simulation of ocean drifters as well, right? So once I have my sort of observing vessels simulated, I can have them sample ocean variables for context. And so here, this is an example showing in a high-res model the gradients of temperature that one of those instruments or part of the marine ecosystem will encounter as they move around. And now, so at this point, I sort of have everything I need from the physics. The next column is the biochemistry and the ecology. I will go a bit faster there. This is one of our marine ecosystem representations in ocean models. This is the so-called Darwin model with, in this case, 51 plankton types. And so we can put that on top of something like echo and simulate the present and future of marine ecosystems on the grid. We've done this at a bunch of resolutions. This model has kind of a detailed penetration of radiation to the sea surface and below, which is key to the simulating of biooptical measurements, like ones carried on BGC Argo. And then on top of this, we have a second generation of ecology model. This is the physiology of it. This is now an agent-based model that simulates something you can put and follow with the fluid, and is going to simulate within itself a distribution of species. And for example, here we emulate the measurement by an experiment that would measure growth rate of a population. So we can simulate sensors that would do that with this sort of models. So now that we have this whole chain of models, we can start doing things with the simulated data. And I'm going to just give you an example after. Summarize the model lineup with this graph. Here's also some links associated with different, again, open source packages that you can right away find on GitHub and use to your convenience. Some of them have to do with dealing with models in Julia, and some others, some other languages. More of the same, and here I might just highlight the Docker aspect. So Docker is something that I'm not going to dig into in details, but it's kind of a computational environment that we can provide you, so you can do these things in a reproducible context. All right. This is my one slide to illustrate or summarize the simulation of ocean robots. So there are two components, basically. The first one is the displacements of the instruments. That can be even a mooring moving a little bit, or it can be something like a drifter. In any case, it's the same equations. You just put what you need on the right-hand side, and that can use low resolution models, high resolution models, statistical models, trained AIs, so on and so forth. And then the second part, all of the bullets after this are things I've already discussed, the simulation of different kind of sensors. Again, we can get quite creative because it's in a virtual world, so we can imagine whatever. Here's the summary of this thought experiment that I was charting earlier. Imagine that you would have a bunch of drifters equipped with miniaturized instruments that would allow you to behave a little bit like an agrocosm and make experiments to get a measurement of the growth rate, for example. So the left-hand side is simulating the vessels, the right-hand side simulating the sensors. I've talked about the infrastructure a fair amount, as you noticed. So this is just to summarize where we are. Essentially, everything that I've told you about, in my mind, is production ready. What's sort of left is to turn these into APIs and then, do the science with them. You can follow this effort by following me on GitHub, for example, or on other social media. But a lot of my stuff goes through GitHub. And to wrap up, I'm just going to illustrate one more thing about the interactivity that I've mentioned to be fairly crucial, because a lot of it is enabled by the work of others, and I wanted to highlight this Mackie visualization package in particular. So this is one of the examples that I picked. Hopefully will let me do that. Yeah. So this is looking at the high resolution model output. 4 kilometers, I think, is the resolution of this model output. It's been discussed before here as well. It's from the MIT GCM, coupled with the GEOS 5 atmosphere. And this has been run by colleagues at JPL for, I think, 14 months. And here I just want to illustrate the sort of the user experience that, a digital twin framework might imply. And so this is just showing you the gradients of temperature. Now these are the ocean currents. And so the point of this is, you have this high resolution model output and you want to deal with it and explore it. And so what I'm showing you here is sort of the sort of things I'd like to be doing, and I think is not possible, as I demonstrate here, is zooming in and out of these sort of high resolution fields. This is a bit laggy because I'm not using the very latest, but this is something I'm quite excited about. So imagine that you're driving this whole chain of models that I'm describing in such ways, right? And one more that's kind of even simpler. This is the same output. This is now just a static plot, but again, with this Mackie package, you get to experience it in ways that are kind of nice, right? And just dig in and out, and this is now, pre-interpolated to a resolution, so you cannot zoom as much. But I don't know. I'm very excited by this. I feel I would highlight it. And that's it for my presentation. The only thing I would say is, all of this is open source and under active development. If you're looking to contribute to open science, here are a couple of places for you to come in if you want. So the Julia Climate and Julia Ocean organization are the ones listed here. And I will stop here. Thank you for listening.
Thank you, Gaël. Sam, do you want to coordinate the questions?
Sure, yeah. I think, Arena, I saw your hand up. I think you're at the top of the line here. Yeah.
Thank you. Super cool. A question, I would be curious if there's an overview paper or a review paper for ocean twins in oceanography. That would be so cool. Or maybe, yeah, ocean twins and in climate applications, or if you know of that kind of literature. But then more specifically, I'm a little bit confused about, so you showed the Darwin ecological model results, and then you are connecting that with echo. I'm a little bit confused. Are you taking physical fields from echo and then driving a biogeochemical module to give you with some initial conditions, to give you are you doing something like this, like a Katiwala type matrix? I don't know.
Yes, I mean, that's a short answer, although we are not using a matrix. We're using, in this case, I'm just running it on top of the echo for the physics. So that means within MIT-GCM. So I'm running it on top of the physics from the physics solution, but directly in the model. So we're not going to a matrix, transport matrix framework, although you can do that. To your first question, I don't know if there is a review on the topic of digital twins in oceanography or climate. I am writing a paper on this, so I will have something to share with you at some point.
You'll have the review.
Well, I'm not quite going to approach it that way, but yes.
Okay.
I see more questions. Maybe.
Yeah, I think Allison was next.
Yeah, can you hear me?
Yep.
Okay, great. Yeah, thanks, Gaël. That was an awesome presentation, and I'm looking forward to kind of looking more at your GitHub packages and all that. I had sort of two questions. One is if you thought of, one of the things that I've heard about digital twins is sort of the ability to bring in maybe human information, human dimensions, sort of stuff. And I don't know, in the context of climate, that usually relates maybe to emissions, but other things. I'm just curious if you have any thoughts about sort of integrating with the human aspect, which can be, I think, more the most uncertain. And then and my second question was sort of more on the sensors and the robots and simulating those within the model. Are you sort of sampling especially for satellites, are you sampling the model to get the derived variable? Are you sort of also, would you be outputting kind of the thing that the satellite's actually seeing and then, sort of recreating that? Does that make sense?
I think so. So I guess the output can be of various levels, right? I mean, one of the ideas is to generate simulated data sets and share them with everybody so that they can then be applied to different kind of estimation problems. The level at which we want to output the data sort of depends, right? If you want to look at something like BGC algo, for example, I think the sort of what I'm doing, thinking about this is, I have the Darwin model and the radiative transfer model in it. I'm going to try and derive the same quantities that are reported by the program.
Right.
So I might choose to output that rather than sort of the more raw variables.
Right, but you're still kind of doing that within the model framework. So it's not just like you're kind of just taking what the model already is outputting for, you know.
Yeah, some of it is really development. You know, we do have these sort of things built to MIT GCM to a degree, but not all of it. So some of the more innovative sensors you can imagine, you know, you have to code them up
Right.
in any way, and then I see value in doing things offline, partly because I want to be able to use sort of some of the high-res models that I'm not going to rerun instantly, so I'll probe the output there. And your first question was about the human dimension, I guess. I guess I'm thinking of the risk components, right? So there's a whole chapter of risk prediction that you could conceive as part of this digital twins framework. That's just not what I'm focused on, so that's why it's not listed. But it is certainly one of the places, like the coastal ocean, for example, is where a lot of this takes place. And the risk prediction there, I think, is sort of the last layer on the rocket.
Cool, thanks.
On mute.
Sam, you're on mute.
Sorry. I was saying, I think we have time for one more question before going into the panel meeting, but then we could, if we have time during the panel meeting and the panelists have questions, we could work that out there. But Xijin Fang, you're next up on the order here.
Gaël, thanks for the nice talk. I have a question, a very general question about the whole concept of a digital twin. So what are the aimed user groups for this digital twin things? So for scientists or for general public people?
So in my case, you know, what I'm sort of after is developing collaborations with the technologists and the people that do like ocean observation per se. But more generally, right, depending on which application you're considering, that could be the end users would be insurance companies, right, if they're focused on the risk prediction, for example. One of the reasons why there is so much traction, I think, behind this concept of digital twin is exactly this sort of applications. It gives kind of it could give an actionable set of information to predict, how to make better business decisions in 10 years, type of things. So that's a completely different space, right?
Yeah.
The third one, I would say, is education. You know, if you come in a classroom with a bunch of code, that's one thing. But if you come in a classroom, even with younger kids, with something they can play and click with, all of a sudden, you know, the interactive dimension of the digital twin framework comes to play.
Yeah, I think the educational rule and also research rule seems make a lot of sense. But for the kind of for business people, industry people going to use the data to do some kind of really real world problem, then the reliability of the representation of the model are going to be very important. So what kind of model they're going to use? I don't know whether there are already some discussion about that. I mean, apparently there are a lot of issues about the ocean we don't know. So how? Yeah. So.
Yeah, totally sure.
Yeah.
Keep forgetting that I'm muted. It's one of those days. Yeah, I wanted to say thanks again to Gaël. Before we move into our private panel meeting. So if you're not on the panel, please depart, and thank you for coming.